Lab. Purpose of this lab is to find the mass of the black hole around which a star revolves using the motion of the star. Fundamental principles we use to do this are the momentum principle and gravitation. Both of these will be built into the code. The system and surroundings are as follows. The star is our system, and the surroundings are composed only of this black hole right here. This green path is the path that the star takes as it goes around the black hole once. And these arrows represent the perpendicular, parallel, and net parts of the force acting on the star. We say here that delta V is equal to V final minus V initial, and that delta P is equal to delta V times the mass of the star. And dP dt is equal to delta P over delta T. And finally, here we say the most important part of it all, F net equals dP dt. Now this dP dt is only the motion of the star, which we're assuming is caused only by the force of gravity from the black hole. Now we break down the change in momentum over change in time of the star into the parallel and perpendicular components. The parallel component is done using p hat times delta p vector, absolute value of the momentum vector over change in delta time, or d time, dt, which we assume is small enough to give us accurate results in between the points that we take. And then here for F net parallel, we say that it's equal to dP dt parallel because, again, we're assuming that there's only gravity acting on the star. So the change in momentum of the star is equal only to the change in momentum over change in time of the star is equal only to the force of gravity acting on it. So the parallel component of gravity is equal to the dP dt parallel, and we use vector subtraction to get that dP dt perpendicular is equal to dP dt, which we found right here, minus dP dt parallel, which is this. And we set the F net perpendicular also equal to dP dt perpendicular. Now the forces on the star are as follows. We have the parallel force in blue and the perpendicular force component in orange. And when we add the blue and the orange, we get the gray part, which if you see right here is nigh equal to the orange because the blue part is just about 0. And the time is given in days. So over the course of around 450 days, we have the force on the star going up and then going back down. And then this is the mass of the black hole as it changes with the distance, the star's distance. And we see that it doesn't really change much other than like small glitches from the code. So we can linearize the mass of the black hole by plotting the net force over gravitational constant times the mass of the star, the y-axis, and plotting 1 over r squared, which is r is equal to the distance between the black hole and the star. And we can see that even if as the radius changes, the net force changes in order to keep this relation linear. And the slope of this line is equal to 8.77 times 10 to the 33. Now what is that measured in? That is measured in kilograms because that is the mass of the black hole. The star here weighs 2 times 10 to the 30, which is just about the mass of our sun. So we can say that the black hole has a mass that is 4,000 times greater than the mass of the star. Now, could the mass of the black hole be different? No, it can't. If the star has only the force, has force acting on it only as a result of orbiting the black hole, and it has the same motion, then the mass of the black hole cannot be different than what we have found here today.